You're looking at real photographs of Jupiter, not digital art, not renders. These were taken from just 4,000 kilometers above the cloud tops. 30,000 frames were returned by NASA's Juno spacecraft, and nearly everyone looks like something no natural world should produce. Patterns that seem engineered, structures that feel artificial. Something incredibly strange is going on inside this planet, and the science behind it may be even stranger. Every image in the JunoCam archive seems to defy expectations of what a planet should look like. Instead of smooth bands or gentle swirls, Jupiter's clouds twist into razor-sharp chevrons, polygonal spirals, and jagged billows that look more like algorithmic art than anything found in nature. The raw data set is immense, over 30,000 frames, each snapped just a few thousand kilometers above the cloud tops, with the camera resolving features as small as 20 kilometers across. Even before any processing, the contrast between bright and dark regions is startling, and the geometry of the cloud structures appears almost too regular to be real. To make the details stand out, scientists apply a modest contrast stretch, about 125% above the original image, to reveal subtle color differences and sharpen the boundaries between atmospheric layers. Outreach versions sometimes push this further, boosting contrast by 150% and exaggerating hues, but even the minimally processed frames retain the same uncanny patterns. The debate over image enhancement is ongoing. Some argue that aggressive processing risks turning authentic weather into digital fantasy, but side-by-side comparisons show that the chevrons, spirals, and crisp edges are present in the raw data, not just in artistic composites. The JunoCam archive is open to the public, and every frame can be traced directly to its original source. No matter how many times the images are reviewed, the same question returns: why does a real planet look engineered? The answer lies not in computer graphics, but in the extreme physics unfolding within Jupiter's atmosphere. To understand how these images were captured and why their authenticity is beyond doubt requires a closer look at the spacecraft itself and the instruments that made this gallery possible. Juno's journey began with a launch from Cape Canaveral on August 5, 2011, setting course for Jupiter with a gravity assist from Earth 2 years later. After traveling nearly 5 years across the solar system, Juno entered Jupiter's orbit on July 5, 2016. Unlike its predecessors, Juno was engineered for endurance and precision. Its 3 solar arrays, each stretching over 9 meters, unfold like wings, collecting sunlight even at Jupiter's distant orbit, where the sun is just a pale disk in the sky. The spacecraft's orbit is nothing like the circular paths of earlier probes. Juno follows a highly elliptical polar trajectory, diving as close as 4,000 kilometers above the cloud tops at Perigove, closer than any mission before. Each sweep lasts just a few hours, but during these passes, Juno captures the planet in razor-sharp detail, revealing features as small as 20 kilometers across. To withstand Jupiter's intense radiation belts, the spacecraft's vital electronics are packed inside a titanium vault, a protective shell weighing nearly 200 kilograms. This shield allows Juno's instruments to survive an environment that would fry most spacecraft within days. The mission's design is built for close encounters. The polar orbit avoids the worst of the radiation, while the brief, high-speed dives maximize data collection and minimize exposure. Every system, from the solar panels to the radiation vault, serves a single purpose: to deliver authentic, unfiltered views of Jupiter's atmosphere. The images and data are not the product of chance or artistic license. They are the result of deliberate engineering choices, rigorous calibration, and a relentless pursuit of accuracy. Juno operates as a precise observer, its instruments tuned to capture Jupiter's true nature, no matter how strange it appears. Jupiter's chevron bands look almost engineered, sawtooth ridges stretching across the planet, repeating with a regularity that seems out of place for a world shaped by chaos. Each chevron is spaced about 1,000 kilometers apart, with individual waves measuring around 750 kilometers from crest to crest and rising nearly 30 kilometers above the surrounding clouds. To understand these geometric patterns, scientists turn to spectral data from Juno's GIRIM instrument. At wavelengths near 2.7 microns, The chevrons glow with the signature of ammonia ice, while the darker lanes between them show a stronger water vapor signal. This chemical fingerprint reveals that upwelling plumes lift ammonia-rich air to the cloud tops, where it condenses and scatters blue light, forming the bright arms of each chevron. Meanwhile, descending air in the dark lanes strips away the ammonia, leaving behind deeper, red-shifted clouds. Dr. Laura Fletcher, who leads atmospheric spectroscopy for the Juno mission, describes the chevrons as a textbook case of wave-driven convection meeting chemical stratification, a synergy that rarely appears so clearly on Earth. The regular spacing and amplitude of these features match predictions for Kelvin-Helmholtz instabilities, where layers of gas moving at different speeds roll up into billows and waves. Instead of smooth bands, Jupiter's jet streams sculpt the atmosphere into these sharp, repeating motifs, each one a visible trace of the physics at work below. The Great Red Spot dominates Jupiter's southern hemisphere, a swirling oval of brick red that even now stretches 15,000 kilometers wide and 12,000 kilometers tall. That's more than enough to swallow Earth whole. But the true scale of this storm goes far beyond its surface. Juno's microwave radiometer has traced the vortex down to depths of at least 200 kilometers, revealing a column of churning gases that pierces through the upper cloud layers into the planet's hidden interior. For centuries, the spot has raged, but in recent decades, its boundaries have begun to contract. Since 1994, the storm has shrunk by about 30%, its edges curling inward, the once elongated oval growing rounder and more compact. Despite this slow decay, the Great Red Spot remains a planetary engine, drawing energy from Jupiter's internal heat and from the powerful jet streams that encircle it. These jets act like invisible walls, trapping the vortex and preventing it from dissipating into the background chaos. High-resolution images from JunoCam show the storm's outer layers unfurling into delicate filaments, shear-driven ribbons that twist and tangle along the spot's edge. As Professor Arjueso describes, these filaments are the clearest visual evidence of shear instability on a planetary scale, a fluid dynamic ballet that can only occur in an atmosphere as vast and energetic as Jupiter's. The persistence of the Great Red Spot is a direct result of this interplay between deep-seated convection, relentless planetary rotation, and the sharp boundaries enforced by the surrounding winds. This is not just a storm, it's a living monument to the raw physics that sculpt Jupiter's ever-changing face. Lightning on Jupiter doesn't just flash in the deep, water-rich layers. Juno's instruments have detected two distinct lightning zones. One is buried near the 5-bar pressure level, and another erupts much higher, just below the visible cloud tops at around 0.7 bar. These shallow flashes are far more energetic than anything found on Earth, each unleashing up to 1 trillion joules of energy. The radio bursts from these storms sweep across the spectrum, and their frequency signatures pinpoint the altitude of the discharges. Where Earth's thunderclouds rely on water and ice, Jupiter's upper storms are charged by ammonia ice, setting the stage for a new kind of electrical storm. But the story grows stranger. In the aftermath of these lightning events, Juno's microwave radiometer picks up pockets of warmth, temperature spikes of 2 to 4 Kelvin above the surroundings. These are the fingerprints of something exotic, ammonia water hailstones known as mushballs. Formed when lightning melts ammonia ice and mixes it with water vapor, these slushy spheres can grow to 1 million kilograms each. Dr. A. Mousies describes mushballs as atmospheric snow gliders, ferrying water to depths where it can affect the planet's internal heat transport. As they fall, they plunge through the atmosphere, carrying ammonia and water all the way down to pressures of 150 bar, far deeper than any storm on Earth. This cycle of electrified storms and mushball rain is not just a curiosity, it is a mechanism that drives Jupiter's chemistry, redistributes heat, and helps sustain the planet's massive, long-lived vortices. At Jupiter's poles, order emerges from chaos. Instead of a single swirling vortex, Juno's close-up images reveal a geometric assembly, a lattice of 12 cyclones, each more than 3,500 kilometers across, arranged with uncanny precision around the pole. The winds inside these cyclones reach 150 meters per second, yet the pattern holds as if locked in place by invisible forces. Beta drift, The tendency of vortices to migrate under the planet's rapid rotation should scatter these storms, but they remain fixed, forming a crystal-like array that persists for years. Magnetic field measurements suggest a deeper connection. Dr. T. Giles describes these polar cyclones as a self-organizing vortex lattice, stabilized by the coupling between Jupiter's magnetic field and its atmosphere. Each cyclone sits at the footpoint of a magnetic flux tube, where auroral currents inject energy, anchoring the storms and maintaining their spacing. The result is a planetary weather crystal, a structure that looks engineered but is born from the interplay of magnetism, rotation, and atmospheric turbulence. Open access to Juno's data has reshaped how planetary science is done. Every raw image, every spectral reading is released as soon as it is processed, available for anyone to study, question, or reinterpret. This policy of transparency has turned Jupiter into a shared laboratory, where discoveries are verified and debated in real time, not just by mission scientists, but by researchers and enthusiasts around the world. The lessons learned from Juno are now woven into the design of next-generation missions like Europa Clipper and JUICE. Both will build on Juno's approach, using open data to accelerate breakthroughs and to encourage unexpected collaborations. The raw textures and patterns revealed in Jupiter's clouds are more than a curiosity. They are a blueprint for decoding the atmospheres of distant exoplanets, where similar physics might paint worlds we have yet to see. In this era, every byte of data becomes a bridge from the strangeness of Jupiter to the unknowns waiting across the galaxy. Jupiter's storms and strange geometry remind us physics can create beauty that defies our imagination. As Juno sends back each new image, we're forced to confront how little we know about chaos on a planetary scale. Mystery remains just 400 million miles from home.